David Can here with another question in topic 1.2. We're looking at uncertainties and errors in the context of data analysis questions. We have a question here where we have a graph of the temperature of an object and its resistance. So we're changing the temperature of the object and looking at how its resistance changes. Based on the shape of the graph, a student hypothesizes that the resistance is inversely proportional to the temperature. We want to use data from the graph to show whether this hypothesis is supported. Before we do that, I'm going to peek ahead a little bit, and we see that in part B, a second student suggests that the relationship is completely different, not inversely proportional. And so that's a clue that we're going to find that the result is not inversely proportional, even though the graph kind of looks like it might be. But let's figure out, let's try and show that the relationship is not inversely proportional. If the relationship were inversely proportional, then the resistance should be equal to some proportionality constant times 1 on the temperature. So whatever resistance value we have and whatever paired temperature value we have, K should be constant. So if we rearrange this to solve for K, we get the proportionality constant should be the resistance at any temperature times that temperature, and that K should be constant for every pair of resistance and temperature. So let's find a couple pairs of resistance and temperature and see if K remains constant. What we want to do is we want to pick a couple of points on this graph that are easy to read and are nice and far apart from each other, more than half of the width of the graph, I would say. So just picking my favorite points, I think this one's pretty easy to read. Coming down, we see that it's between 250 and 300 Kelvin, so that's 275 Kelvin. And the resistance is 3/4 of the way between 4,000 and 5,000. That would be 4,750 ohms. So that's one point. We need another point that's nice and far away from that. I am a little bit partial to this one. The x-coordinate's a little bit harder to read. It's 1/4 of the way between 350 and 400. So that's 350 plus 1/4 of 50 for 362.5. And then the height is 1/4 of the way between 0 and 1,250. So those are our coordinates: 275, 4,750, 362.5, and 250. What we want to do now is we want to see if K remains constant. So for the first point, where we have 275, and for the resistance it was 4,750, is that the same as this other proportionality constant where the resistance is 250 and the temperature was 362.5? So are these the same? When you punch them into your calculator, you get that the first one is about 13 million, and the second one is just 91,000. Very, very different. Clearly not close to the same. So we can say at the end, K1 is not equal to K2. Therefore, R is not inversely proportional to T. Okay, so then another student comes up and says, well, if R is not inversely proportional to T, what about this relationship? Is the natural log of R equal to some constant plus some other constant divided by T? What the student has done is they've replotted the data on a new graph with new axes. Error bars are included. These axes are 1 on T on the x-axis and the natural log of R on the y-axis. We're asked to explain how the graph shows evidence to support the student's suggestion. Well, the first thing that we want to do is we want to look at this equation and recognize that this is an equation of a straight line. If we take our standard form of a straight line y equals mx plus c. And compare that to what we have here. We can see that if we rearrange it just a little bit, the natural log of r equals b times 1 on t plus a. We can see that all the elements line up. If our y variable is the natural log of r, and our x variable is 1 on t, then slope is this constant b, and the y-intercept is this constant a. So if we put 1 on t on the x-axis and the natural log of r on the y-axis, we get what should be a straight line. And then when we look at the graph, we see that a straight line does go through all the data. So there is a straight line that fits all the error bars, and the equation predicts that a straight line should fit. So that's evidence that, that the equation is a good model for the data. So the equation suggests that when 1 on t is on the x-axis and the natural log of r is on the y-axis, a straight line should be produced. And then we can see that a straight line does fit through all the data's error bars, supporting the student's theory. Finally, we want to use the graph to determine the constants a and b. How to do that, we've already figured that out. We've already figured out that a is going to be the y-intercept of the graph, and b is going to be the slope of the graph. So all we have to do is go back to our graph and pick out that information from the graph. Now, I'm not sure that I like this best fit line that I've sort of sketched in quickly. Some of the things that I don't like is that there's a pretty clear trend of the data below and then above, and then we're starting to head below the line again. To me, that's indicating a kind of a poor fit. I'm going to try to draw another one, see if I like it a bit more. Okay, I think we're getting there. Just need to bring this side down a little bit more, I think. All right, I'm liking this one a little bit more. We're pretty much on all the data, with the exception of this last one, but we're still within its error bar, and that's critical. We'll go with this one. And with these kinds of questions, you're going to be given a range of acceptable answers for the slope and the y-intercept, so hopefully we're within that range. We'll pick out our y-intercept, so that's 2.1, so 10 delineations between -2 and -3. So A, which we said is our y-intercept, is going to be -2.1. The units for that look like they're going to be log of ohms, natural log of ohms. That's a kind of a weird unit. I don't expect that credit would be required for that unit. Next we need the slope, so we need to pick 2 points that are reasonably far away. Well, this one's nice and far away. That's 0, comma, negative 2.1. And yeah, this one is as far away as you can get. You need to be using at least half the graph. Here we're using the whole graph, so that's perfect. Looks like this is 4. But remember, you always have to come down and check the scale. So that's actually 4 times 10 to the negative 3. And the height looks like it's 3 minor delineations up from 4, so that's going to be 4.3. Okay, so for B, we just need the slope. The slope is going to be rise over run. So y2 and y1, those are the vertical components. So that's 4.3 and negative 2.1. So 4.3 take negative 2.1. And then the run is 4 times 10 to the third and 0. All right, so you'll type that into your calculator, remembering that a double negative is a positive, so that's 4.3 plus 2.1. And what you should get is 1,600 to 2 significant figures. The units are a little bit weird again. We have our y unit divided by our x unit. Our y unit we already said was log of ohms, and our x unit is Kelvin to the negative 1. So that's natural log of ohms per Kelvin, which is really just log of ohms Kelvin. I don't expect that credit is given or even that you need to list the units for this question, because the units are so weird, but I think it's best to just be in the habit of attempting the units anyway, because you just never know.